Bonjour, ça va? Je m'appelle Vanessa, and today I'm going to be talking about acids and bases. So the four standards that I'm going through will be going through the theories of acids and bases, the properties of acids and bases, strong versus weak acids and bases, and finally the pH scale, the logarithmic pH scale. Our acids and bases unit is based on 4 different standards that I will be going over in these videos. First, the first standard, standard 8.1, is focused on the theories of acids and bases. As you can see, we have 3 different theories: the Arrhenius, the Bronsted-Lowry, and the Lewis theory. The very first one developed by scientists was the Arrhenius. And the Arrhenius acid and base theory was based on the dissociation of acids and bases of their ions into ions. As you can see here, our acids will dissociate into H plus ions, and our bases will dissociate into OH minus ions. Our next theory was later developed. It's called the Bronsted-Lowry theory, and it's based on the the fact that acids and bases are donors and acceptors of protons. As you can see, Bronsted-Lowry and Lewis theories, they're both later theories, and they're much better explain the concepts of acids and bases. And currently scientists use Bronsted-Lowry and Lewis rather than Arrhenius. So our Bronsted-Lowry, the acid acts as an H plus donor, which I will write in red. And then our base acts as a H plus acceptor. And then our final concept is the Lewis theory. And the Lewis theory encompasses the Bronsted-Lowry theory, and oftentimes they're referred together in conjunction. Right here is a diagram of how the Lewis theory works. It's a theory based on the fact that Lewis acids and bases are electron pair acceptors and electron pair donors. So our Lewis acid accepts, so in this diagram our Lewis acid, which is right here, accepts the electron pair. And our Lewis base right here, as you can see, our lone pair gives this electron pair to our boron trifluoride. And the reason that happens is because our boron trifluoride has an incomplete octet, so it can accept this, this lone pair. The reason why this is important in our acid and base theory is because electron pairs are needed to bond the H plus ions. So as you can see, there's a gradual evolution of acid and base theory, from dissociation of ions to the actual electron pairs that cause the bonding of the H plus ions that are so important, and what makes acids and bases acids and bases. Okay, for our Bronsted-Lowry, what is also really important is, of course, our conjugate acid and our conjugate base theories. As you can see, Bronsted-Lowry allows us to think about the theory of conjugate pairs. So the best way to understand this is, of course, to start with an example. So first we have our HNO2, which is an acid, as you can see. So what I would like everyone to try is to, based on what we know about Bronsted-Lowry, about the fact that an acid is an H plus donor, what is the conjugate base of this Bronsted-Lowry acid? So just pause the video and try that. Okay, welcome back. So we're trying to, so like I discussed before, this is an acid. So its conjugate base would, of course, involve the taking away of a H plus ion. So what does that leave us with? And this should be our conjugate base for our acid. So that is also one of our standards, the ability to identify conjugate bases and acids and bases and conjugate acids. Okay, so after we accomplish this, let's try to do this again with a conjugate acid, which is basically the same thing but in an opposite manner. So we have our CO3 2-. So as you can see, this is a base, a bronze latter base. So pause the video, and I'd like to try for you guys to all try this and write the conjugate acid. Okay, welcome back. As we have our base, what do you know about bronze latter bases? That they are H+ acceptors. So what does that mean? Since we have, it's an H+, we're accepting an ion, right? We know it's CO3. And then also, since they're accepting an ion, it should be negative. Because if it's positive, it's becoming more positive. So it goes from -2 to -1. Because of the +1 charge of the H+ ion. Okay. And then let's combine these two things and start with a actual finding the conjugate acid and base from the following reaction. So we have here our NH4 plus H2O yields H3O plus NH3. Okay, so right here we have a reaction, and what I want is to identify our acid bases, and then in response our conjugate base and conjugate acid. So I don't know if you guys know this, but our H2O, water, can be amphoteric. And as an amphoteric compound, it can act as an acid or base. So first, let's identify the different species. We have H2O and H3O plus and NH4 plus to NH3. So as we have NH4 plus, we can assume that this is our acid. And then this will be our conjugate base. Because as we know, yet again, that as an acid, it donates an H+ ion. And an H+ ion is donated because the ion is donated and it turns into NH3. Yes. And right here we have our base. And it's amphoteric, so right now it's acting as a base, but H2 can also act as an acid. And as our base, we know that it is an H+ acceptor. So this is our conjugate base and our conjugate acid. Because as you can see, the base, this accepts an H+ ion. And instead of H2, it becomes H3. Okay, as an acid and as a base. So that's an example. So now I want you guys to try also. I will write a reaction. I would like you guys to identify the acid, the base, and the conjugate acid-base pairs that are respective to them. Pause the video, please, and try this. Okay, welcome back. As we look, we can see this is an acid, and this should be our base, but in a different reaction, we may not be sure because it's amphoteric. As a result, we want to determine which one is our conjugate acid and our conjugate base pair. So, as an acid, it should donate a H+ ion to our conjugate base, which will accept and I'll draw a line to indicate this. And then our base, we have our conjugate acid. And that should be the answer to this problem. All right. So, our next, okay, yeah, pause it.
Just go ahead, you just have to cut out a little bit.
Okay. Hi everyone, welcome back. We're still talking about acids and bases, but now we're on to the properties of acids and bases. Now, we can define acids and bases in a lot of different ways. One of these ways is the ease of losing and donating a proton, which is how we distinguish strong acids and bases from weak acids and bases, which I'll go on further later. However, there are three main characteristics of acids and bases. So first of all, they dissolve in water. They dissolve in water to give a solution with a pH of less than 7, which makes it acidic, or greater than 7, which makes it basic. That is one of the characteristics of an acid and base. The next one is that acids react with bases to give a salt and water. They react with each other. And the last characteristic is the fact that they can be distinguished by different litmuses or indicators. Indicators, yes. Okay, so further on the fact that they react with each other. So right here, we have the three main types of acids and acid reactions. So we have acid plus a metal, acid plus a base, which is the most common one, and acid plus a carbonate. This is the one you'll probably encounter most on tests. So for an example of an acid plus a metal, here is our reaction. We have hydrochloric acid plus our metal, which should yield, if we do a switching, right, a salt plus our hydrogen. That is our first. And we have to make sure everything is balanced. As you can see, there's 2 hydrogens, 2 chlorides. And there's 2 chlorides on this side, and also 2 hydrogens on this side. And so everything is balanced, and this is an example of an acid and a metal reaction. Now we have our acid and base reaction example. Yet again, I'm using hydrochloric acid, which, if you want to, you can distinguish it by using aqueous. So for our IB tests, it's not really necessary for a lot of questions to actually put the, if it's aqueous or solid or in solution. Only if they tell you that you should, then you should put it. Okay, so our base, we'll use NaOH, a very common strong base, which then will yield our salts. So if we use it, if we do like a switching reaction, we have our sodium chloride plus our water. So let's check if everything is balanced. It looks good to me. Okay, and finally we have our acid and carbonate reaction. Okay, so I'm using hydrochloric acid again, plus our carbonate, calcium carbonate, which should yield a calcium chloride, a salt. As you can see, our salts usually have chloride for their anions, right? Plus, of course, H2O and CO2. Okay, now all of these are different reactions, and everything looks pretty balanced to me. If you need a review on balancing equations, it's very simple. You just have to make sure that all your different products and reactants have the same number, because the number, like let's say there's 2 here, indicates the number of moles, and those have to be balanced in order for you to get full credit on whatever exams you're taking. Okay, So what we're talking about next, another point is also the differentiation between alkali and bases. So alkalis are bases, but they're soluble bases. And they have OH minus, they're defined by the OH minus ions, and bases, they accept H plus. So alkalis are a subset of bases. They're like a type of bases. And it's really important to know the distinction between alkalis and bases. Okay. What we're talking about next will be about our different indicators, our common indicators. So I'm assuming a lot of people have done titrations, have done different labs using different common indicators. And a lot of these you just have to memorize. It's assumed that pink will be acid and then blue will be base, and this is common in a lot of titrations and stuff, but you can't really assume this because there are a variety of different indicators that have all sorts of characteristics. So let's talk about a few common ones. We have methyl orange. Methyl orange is a common one. We also have bromothiamyl blue. Bromophenol blue. And let's talk about phenolphthalein. Which is a very kind of long. So for our methyl orange, our acid, let's just draw a chart here, our acid and base. So for methyl orange, our acid is going to turn red, and our base will turn yellow. For bromophenol blue, not bromothiamyl, as I said before, bromophenol, our acid will turn yellow, and our base will turn blue. And that's important to remember. And for our phenolphthalein, for an acid, it shouldn't have any color, colorless. And then our base will be red. So I said before bromothiamyl blue, and bromothiamyl blue is different because it's not actually that different from bromophenol blue. The acid will still turn yellow, and the base will still turn blue. So bromophenol and blue and bromothiamyl blue have the same color changes for our various acids and bases. And these things are just things you have to memorize because there might be questions that ask about different reactions or different titrations or whatever, and you want to know about whether you have an acid or base or what colors will change for the indicators. Because that's how you differentiate our acids and bases. Okay, so for our next point, let's talk a little bit about our strong and weak acids and bases. As I said before, it's basing on the ease of losing and donating a proton. Okay, and it's also based on how much dissociation is. So if our equilibrium is on the right, our equilibrium is on the right, then it will dissociate entirely into ions. As you can see, let's have an example of a really strong acid that I've been using in our, a really strong acid I've been using recently before the different reactions of our acid-base acid carbonate, HCl, hydrochloric acid. And as you can see, if you have a reaction, it will dissociate completely into ions. And our equilibrium is on the right. So also, on another video, my friend Courtney will also be talking about equilibrium and how this is relevant. If the equilibrium is on the left, right, then right here you have, or in the products, then this would be a weak acid. Okay? And there are certain strong acids and strong bases, or weak acids and weak bases, that you just have to memorize. There isn't really anything you can do about it. It's just something you have to think about if you're taking AP exams or IB exams or whatever. So here are some strong acids that are really important. So for these acids, it'd be really convenient if you knew all your polyatomic ions, because that will really give you a better understanding. Okay? So here are some strong bases. So our hydrochloric acid, like I referred to before, our nitric acid, and our sulfuric acid, all with very low pHs and all things that you have to know. Now let's talk about some of our strong bases. Okay, so right here we have our lithium, our sodium, our potassium, and our barium hydroxides. So lithium hydroxide, sodium hydroxide, potassium hydroxide, and barium hydroxide. And these are our strong bases. They all have OH on them, which is good to know and good to memorize. Right here. Okay? And then now we have our weak acids. And a few examples. Carbonic. And finally, phosphoric. Okay, so this is ethanoic acid, this is carbonic acid, and this is phosphoric acid. And these are some examples of weak acids. And there's really nothing you can memorize. You just have to, there's nothing you can just figure out. You have to memorize it completely. Okay? And I'll leave this up, and I'll also have some examples of weak bases. Our ammonia and our ethylamine are some examples. So this is our ammonia and ethylamine. It'd be really convenient if you could just identify these in different problem sets. Okay? And there are also certain things you have to know about distinguishing weak and strong acids and how to do that, right? So here are our 3 points. Okay, so one of the first things you can do is distinguish by electrical conductivity. Now, why does this happen? How can you do this? Why does this work? Electrical conductivity, because if you have a strong acid, if it dissociates completely into your ions, then that means that it will conduct electricity. And as a result, you can differentiate strong from weak. But however, a weakness of electrical conductivity, you can't differentiate whether it's whether it's an acid or a base, just whether if it's strong or weak. Okay? And our next one is the rate of reaction. And finally, we can also differentiate through pH. If you think about rate of reaction, it's just that if it's a strong acid or base, the rate of reaction should be a lot faster.